All right, so today's notes are on theorems about roots of polynomials. Our content objective is to solve polynomial equations using the rational root theorem and the conjugate root theorem. And our language objective is to use the correct terminology to explain those theorems. So first thing we're going to delve in with is the rational root theorem. So what the rational root theorem says is that if you have a polynomial with integer coefficients, which integer, if you forgot that vocab word, is just positive or negative whole numbers. So as long as all the coefficients are positive or negative whole numbers, then you can use this rational root theorem. And what this says is that there are a limited number of possible roots. If you forgot what roots are, these are our zeros, our solutions, our x-intercepts. So there's a limited number of possible x-intercepts, zeros, roots, if we have all integer coefficients. And what we know about these possible roots is that any integer roots must be factors of the constant. So the constant, again, is the term with no variable in your polynomial. So integer, positive, negative, whole number roots must be factors of the constant, the term with no variable. Rational roots, so this is the key thing for the rational root theorem, rational roots, which are basically fractions or numbers that can be written as fractions, must have a reduced or simplified form of p over q, where p is a factor of the constant and q is the factor of the leading coefficient. So leading coefficient is the number that's the coefficient of the term with the highest degree, if you've forgotten that. So q is a factor of the coefficient of the term with the highest degree. So I know that's a lot of information to take in and sort of parse out what it means, but let's delve in so you can see a visual of what we're talking about and see if that makes some more sense. So our first example asks, what are the possible rational roots of 2x cubed minus x squared plus 2x plus 5 equals 0? First thing we're going to determine is the possible p-values. So our p-values, again, are the factors of the constant. So our constant here is 5. So p is going to be all of our factors of 5. So the only factors of 5 are 1 and 5. So I could have positive 1 and positive 5, negative 1, negative 5. Those are my possible roots of this positive 5 value. So all my possible p-values are plus or minus 1 and plus or minus 5. My possible q values are the factors of the leading coefficient. So the leading coefficient, again, is the coefficient of the term with the highest degree. In this example, that's 2. So again, p was 5, q is going to be 2. Factors of 2, again, are plus or minus 1 and plus or minus 2. So those are all of our factors of p and q. So then the last bit, our possible rational roots are going to just be all the p values or all possible p over q combinations. So my last step is going to be write a list of possible p over q values. So p over q could equal 1 over 1, so plus or minus 1, because 1 over 1 would just be 1. It could be plus or minus 1 over 2, plus or minus 1 over 2. It could be plus or minus 5 over 1, which is just 5. So 5 over 1 would just be plus or minus 5. And then plus or minus 5 over 2. So this would be our answer. These are all of the possible rational roots. So these are all of our possible rational roots for this polynomial based on the rational root theorem. All right, so you probably are wondering, why are we going to learn this? How is this going to help us with polynomials? What we can use this for is to actually solve out our factor and solve out our polynomials when it's not always evident how to factor it or what we can do to simplify it. So our next example asks us, what are the rational? So the last one asks us the possible rational roots. This example wants us to actually solve out all of the possible rational roots, or actually solve out for the rational roots of 15x cubed minus 32x plus 3x plus 2 equals 0. So what are the rational roots of this polynomial? So the actual rational roots, not just the possible rational roots. We're still going to start by determining the possible rational roots. So I'm going to determine my p and q values, or possible p and q values. Possible p and q values / factors. So for p, again, this is the constant term. So possible factors are plus or minus 1, plus or minus 2. Q has a few more factors this time, so Q is 15. So possible factors of 15 are plus or minus 1, I'm going to go in order from least to greatest. So then plus or minus 3, plus or minus 5, plus or minus 15. So these are all my possible factors of 15. So those are all my possible Q values. So then my next step is determine all the possible rational roots. So again, these are my P over Q values. So I again have plus or minus 1, plus or minus 2. So I'm going to do 1 over 2, plus or minus 1/3, plus or minus 2/3, plus or minus 1/5, plus or minus 2/5, plus or minus 1/15, plus or minus 2/15. So that's a lot of possible roots. But what I'm going to suggest for our next step as we start trying to whittle down which ones are the actual rational roots is always start with the whole numbers because those are a lot easier to work with. So now we have a finite number of possible roots. We have 2, 4, 6, 8, 10, 12, 14, 16. 16 possible roots that could be solutions to this polynomial equation. So we have 16 possibilities that we've narrowed it down to from infinite, so that's a pretty good start. I know it might seem like a lot for now, but it makes it a lot easier. So we're going to test our possible roots until there is one, sorry, that's 2 words, is one that works. So there's 2 ways that you could do this. You could plug these into your original equation for x and calculate it out. So you could plug each one into x and calculate it out. Or you can use our other theorem that we learned about, the remainder theorem, which tells us that if we use synthetic division for this, we can, if there's no remainder, then it is a factor, or that, sorry, if there's no remainder, then it is a factor. So let's try 1, which would actually be, so -1, which when I use synthetic division would be 1. So I'm going to do 15, -32, 3, 2. So I'm going to see if this one works. And if you don't know what I'm doing synthetic division to see if -1 is a factor of this value. -14, -14, -12. So this one does not work. So then I'm going to try 1. So then I'll do -1. And again, I have 15, -32. If you're not, sorry, I'll draw a little dividing line here. But I'm just dividing out using, or evaluating each one using synthetic division. If you prefer to plug these values into your equation, you can plug in or use synthetic division. So I'm choosing to use synthetic division because I think this will be easier. So this would be -47. So that one doesn't work either. I can keep going. So then again, I'm always trying my whole numbers first. So I tried plus or minus 1. Now I'm going to try -2. So I'll have 15, -32, 3, 2. Same coefficients every time. 30, -2. This would be -4, -1, -2. And look at that, we have one that works. So -2, this one didn't work. This one indeed does work. So I found one of my factors. So I can write my new factored form. So this is another benefit to using synthetic division. If you didn't use synthetic division to start, then you'd have to now synthetically divide to get your new equation. But my new equation is going to be 15x squared minus 2x minus 1. And then I know that would be multiplied by my factor x plus 2. So I know x minus 2. It's a negative 2, sorry. So x minus 2. So I know these are my factors now, and I can keep factoring it to write my fully factored form. So my next step is fully factor. So if you forgot how to use middle term splitting method, you do first times the last term, and I get 15x squared. Factors of negative 15 that add to 2 are negative 5x, positive 3x, and then I'm going to use my grouping method. So I have 5x times 3x minus 1, and then plus 1, 3x minus 1, and I have 5x plus 1 times 3x minus 1 times x minus 2. So that's my fully factored form. Now I'm going to use the ZPP, zero product property, to solve. So I can say 5x plus 1 equals 0, minus 1, 5x equals negative 1, so x equals negative 1/5 is one of my solutions. 3x minus 1 equals 0, add 1, x equals 1/3, and last but not least, x minus 2 equals 0, so x equals 2. So now I've fully solved this polynomial that we started with simply by using the rational root theorem and factoring it all the way out. All right, so last thing I want to cover is the conjugate root theorem really, really quickly. So the conjugate root theorem we're going to spend some more time with this in class, but all this says is that if a plus the square root of b is a root, then so is a minus the square root of b. So if conjugates are always going to be roots, so if you have a positive one, then the conjugate would also have to be a root. This is similarly true for imaginary solutions. So if a plus bi is a root, then so is a minus bi. So our only quick example we'll do today is that if a quartic polynomial has roots square root of 2 and 1 plus I, what are the other roots? So all you're going to have to do is do the negative or positive version. So this would be like 0 plus root 2. So the other possible root for this one would be the negative square root of 2. This one, since it's positive here, the other one would be negative. So the other possible roots are just negative root 2 and 1 minus I. If you want to see how we can actually use this to build equations of polynomials, I'll record a separate video for that. But that's all for today. Make sure you write down any questions, comments, or concerns so we can go over them together in class.